What we really want to figure out is how we calculate work and what the result of doing work is. So today we're going to focus on the definition of work and its connection with energy. So first, I want to remind you of a few things. And one is the definition of work, that it's the method by which you can change something's energy. It's the definition I gave on Friday. I'm reiterating it today. It's the method by which you can change something's energy. The truth is, there's only two ways to change a system's energy. Only two. In all of nature, you can only add energy or take energy away in two ways. The first is by doing work. And it's probably better to say mechanical work, because what we're talking about here is mechanical work. There are other kinds of work, but we're focusing on mechanical. Mechanical simply means motion. At the same time, you can also change something's energy by allowing heat to flow into it or out of it. Those are the two methods that you can change something's energy. We talked a little bit about how heat can change energy on Friday. Today we're going to focus on the mechanical nature of work. And so let's start with the technical definition. I'm going to continue to write work out so that I'm not using a capital W, and that's simply to not confuse it with weight. By definition, work looks like this. Technically, this is what I'd like you to know. This is not just straight multiplication. And for those of you who don't understand subtlety, this is not me trying to emphasize that you're multiplying. This is actually supposed to be a larger than normal size dot because it's called a dot product. Sometimes called a scalar product. So for all of you guys who are in mu alpha theta, and our mathy math folks, you can't just multiply vectors together like they're numbers. Vectors have direction. And because of that, the direction prevents you from multiplying them the same way you would multiply two numbers together. There's different ways to multiply vectors together. The first way is called the scalar product or dot product. It produces a scalar as a result. Now, that's not why this one is used. I'll explain why this one's used in a moment. But the dot product takes two vectors and produces a scalar. There are other vector products. The other one that we will use this year is called the cross product, which will produce a vector as a result. But the dot product and cross product are the two ways in which you can multiply vectors. The dot product is important because what this dot actually means is the force in the direction of the displacement. That's what it's saying, and that's what you should get into your notes. That this product is not a product of the force and the displacement, but it's a product of the force that's in the direction of the displacement with a value for the displacement. That's not necessarily obvious or easy to understand. So as an example, consider a wagon. If I have a wagon and I'm applying 150 newtons of force to it along its handle at maybe an angle of 30 degrees, it should be clear that the wagon is likely to roll along the ground. So it will have some displacement, let's say 5 meters. The 150 Newton force, though, isn't all being used to move the wagon. Only a portion of it is being used to move the wagon. When calculating the work done, it's the portion of the force that is in the direction of the displacement that does work. We know that this 150 Newton force has two components. Two components that can be used in this calculation. There's the horizontal component and there's the vertical component. the vertical component isn't helping the wagon to move to the right, and therefore doesn't do work in causing the wagon to move. The horizontal one does. This is what we mean when we say the work that is in the direction of the displacement. I'm sorry, the force that is in the direction of the displacement. This is sometimes written in your textbook as the force parallel to the displacement. Sometimes that's how your book writes it. They put a little parallel symbol there. Now you guys who are shrewd at all realize that this angle obviously plays a role in determining the force here, the amount of force that's in the direction. And it should be pretty easy to figure out how much is there. For the mathy folks, you guys are already ahead of me. You realize that this is going to be F cosine theta times delta x. But we just write this whole thing out as F delta x cosine theta. This is generally how the equation for work is written on most equation sheets. We say the work done is the force times the displacement times the cosine of the angle between them. Now, take a few moments and just practice. Calculate how much work is being done by this force on the wagon. All right, you guys should be done by now. So we multiplied this out. We got 650. The unit for force is Newton. The unit for displacement is meter. So technically it'd be 650 Newton meters, but these have been given a different name. It's 650 joules of work. Now, I asked this question all day, and I've gotten a mixed set of results. How do we know if this work changed the energy of the wagon? What's an easy thing we can look at about the wagon to know whether its energy has changed or not? Yes, sir? That's right. That's the simplest way to know whether this amount of work actually changed its energy. The only form of energy we've even talked about has been kinetic energy. And although we've said that there are other forms, thermal energy and such, in this example, if we want to know whether this work changed the energy, we'd look to see whether the wagon was moving or not when we were done. Kinetic energy is the only kind of energy we actually know about right now. And since kinetic energy is 1/2 mv squared, the most outward way of knowing whether the wagon has more energy than it had before is if it's moving. Finding and tracking energy is important here. But I want you to know something that we don't know whether the wagon actually has more energy now than it did. We know it's 5 meters away from where it was, but there's no way to know whether it actually has more energy. There's not enough information given here. For example, this is the work done by one force acting on the wagon. Are there other forces that are likely acting on the wagon? Let's name some of the forces that are likely acting on the wagon. What's another one? Friction is likely acting on the wagon. Another one? Gravity is another one acting on the wagon. Another one? Normal force, likely acting on the wagon. These are all forces that are likely acting on the wagon. And all of them could be doing work on the wagon. Positive work increases an object's energy. Negative work takes it away. These forces could be doing things to the wagon as well, taking or adding energy to the wagon. Now, truthfully, if you're really paying attention to the things I've said, then you know that two of these forces aren't doing any work. Can anybody name one? Oh, that makes me sad. Yes, ma'am? Normal and the weight. That's right. They can't do any work. The simplest reason is that they are not in the direction of the motion of the wagon. Right? The cosine would be of 90 degrees, and a cosine of 90 is 0. So the truth is, normal and weight aren't doing work here. But could the friction do work? Let's take a look at the friction and its ability to do work here. If I look at the direction of motion, this yellow big bold arrow is definitely the direction the wagon would be moving under the action of the force, the 150 newtons. What is the angle between the yellow arrow and the friction? Yeah, from here to here is 180 degrees. So if I wanted to find out the work done by friction, I don't even know how big the frictional force is. I do know that I would have to take the cosine of 180 degrees to calculate this work. Because there's 180 degrees between the displacement and the friction. I'm bringing this up because you guys have been practicing that unit circle, so you should be able to tell me what the cosine of 180 degrees is. That's right, it's -1. It's always -1. This is important. That means that any work done by friction, which will always be against the direction of motion, will always be negative. Now that's kind of going to be important here. That friction can only act to take away mechanical energy. That's why if you pull a chair 5 meters across the room, the chair probably doesn't still have that energy. Friction probably took that energy away as you were giving it to the chair. You pull on the chair, it starts to move across the room, and friction takes that energy away just as fast as you can give it to the chair. That's when you stop moving the chair, stop holding the chair, you let go, it stops moving almost immediately. Why? Because friction was draining the energy away the entire time. The only way you can change something's energy is if you do net work on the object. I'm introducing a new vocabulary word here. The only way you can change something's energy is if you do net work on an object. Net work refers to the sum of the work done by all the forces acting on the object. Net work is the sum of all the forces acting on the object. But before I change slides, let me just be very over the top here. Any force can do work. That doesn't mean that it's changing the energy of the object. Individual forces can change the energy of an object. It doesn't mean that they do. The only way to know if an object's energy has changed is if net work was done on the object. Now, I need to be very careful about the way I state this. There are different ways to change an object's energy. We are currently focused on the one observable kind of energy, kinetic energy. So when we talk about this, we're talking about making the object go faster or making the object go slower. Positive net work means the object's going to be going faster. Negative net work means the object is going to be going slower. An object can't have negative energy. It can have zero energy. But it can't have negative energy. Not in a traditional sense. So, for you math types, I want to derive something for you. This is mostly because I think that some of you appreciate seeing things that connect to other things you've done. And I want to start by reminding you that net force can lead to an acceleration. Newton's second law. Now, when you have a net force, an unbalanced force, that can lead to an acceleration. For the time being, let's assume that this net force is in the direction of motion, and that our object isn't changing direction. Does that make sense? So I don't know what all the forces are that are acting. I do know that this isn't causing the object to turn. It's causing the object to get faster or to get slower. By definition, net work should be the work done by the net force. I'm dropping the cosine because we already just said that we're dealing with a force that's in the direction of motion. That's why I'm leaving out the cosine. Now, the first thing I want to suggest is that we can substitute MA in for net force and write the net work as MA times delta X. Part of the reason I bring this up is we've seen A delta X before in one of our motion equations. If you don't remember, think V final squared minus V initial squared equals 2A delta X. So 1/2 V final squared minus V initial squared equals A delta X. Good so far? So I can substitute and get net work equals M times 1/2 V final squared minus V initial squared. I hope it's obvious what we're going to do next. I'm just going to distribute, which means that net work equals 1/2 M V final squared minus 1/2 M V initial squared. You guys see that? What are these? What is 1/2 MV squared?
Kinetic energy.
That's right. Thank you. This is called the work energy theorem. And it says that the way to change something's kinetic energy is to do net work on it. The work energy theorem. The way to change an object's kinetic energy is to do net work on it. So if you didn't pay attention all the way to the end, this is where you really should pay attention.
The way to change an object's energy.
Kinetic energy is to do net work on it. Now, it might not be obvious, but this should look an awful lot like doesn't it? These form two sides of kind of the same idea. Impulse was the change in momentum. Net work is the change in kinetic energy. Although energy and momentum are not the same measurement, they work together to give us a picture of what's happening to objects. It is important that you know that work is a scalar, though, and impulse is a vector. It's very important that you keep those straight. I also want to point out something that you might not remember. If I have a graph of force and time, What's the area under this graph? Do you remember? Oh, it's on the last test. Well, the change in momentum. The area under the graph is the impulse, or the change in momentum. It's important because it allows us to find a way of calculating impulse if the force isn't constant. It should be pretty clear that I can do the same thing with position and force. If I have a graph of position and force, for the area under this graph will be the net work, or the change in kinetic energy. Good so far?
So wait, if it's force and then what's the other one?
Position.
So that's like change next again?
Yeah. Also, do you understand how easy it can be to swap these two on a test? If you're not very careful or watching very closely. Force versus time is impulse. Force versus position is energy. Of course, there was a question on last year's test that mixed the two of them up. That was lovely. All right. Let's do a couple other example questions just to kind of get this. The next example question I think we're going to do is one that I want to be straightforward and easy. Let's see if it is. We're going to go to a kind of a schematic example, a box. And we're going to say that there's 20 newtons of force acting on the box at an angle of 20 degrees. At the same time, there's a frictional force of 5 newtons acting on the box. And lastly, the box has a mass of 2 kilograms. You guys got all those specifics? I'm going to ask you 4 questions. I think they're relatively straightforward. Let's see. Question A. How much work does the 20 Newton force do? Question B. Same question, but the frictional force. Question C. What is the net work? Question D. How fast is it going? Assume the box starts from rest and is moved 10 meters along the ground under the action of these 2 forces. Again, assume it starts from rest and is moved 10 meters along the ground due to the action of these 2 forces. So just real briefly, 188 joules. What you guys got? Good, good, good. Negative 50 joules. So 138 joules. And then 138 equals 1/2 mv final squared. So, want me to walk through them a little bit? We'll start with A. If I want to find out how much work the 20 Newton force does, work is going to be force times the displacement times the cosine of the angle. So that will be 20 times 10 times the cosine of 20 degrees. How's that? Pretty good? So that gets me 188. If I want the work done by friction, that work will be my 5 newtons times my displacement of 10 times the cosine of 180 degrees. That just makes it negative. So negative 50 joules. C, the net work is just the sum. 188 minus 50. So 135 joules. And then lastly, the work energy theorem is net work equals 1/2 mv final squared minus 1/2 mv initial squared. So for net work, that's going to be the 135 joules equals 1/2 times 2 times v final squared minus 0. Started from rest. Yes, it should be 138. Thank you. So that means v final is simply the square root of 138, which is what, just a little bit less than 12. Well, 11 point what?
74
Meters per second. Questions about this? Remember, if you know something's energy, you know how much work had to be done on the object. That's an important piece of information. Just like if you know something's change in momentum, you knew how much impulse it had to experience. If you know an object's change in kinetic energy, you know how much net work had to be done. All right, that's it for today.